Hello everyone and welcome to our webinar 3D Printing in Medicine. My name is Jasmine Wild and I'm a digital marketing specialist at Stratasys MakerBot EMEA. I'm happy that you're all here and let me introduce you to our presenters today. We have Dr. Jochen Zimmer. He's a senior sales engineer at Stratasys MakerBot division. And Dr. Florian Thieringer. He is MD, DDS, MHBA at University Hospital in Basel. Welcome to you all. Before we start, I would like to brief you with some quick housekeeping notes. So if you have any questions, please use the chat box or the question box. And there will also be time for a Q&A session at the end of the webinar. And of course, a recorded version will be sent to you all afterwards. So I will hand over to Dr. Jochen Zimmer right now. And our agenda, I just skipped this agenda right now because I'll just hand over. Thanks. So.
Okay. Hello. Thanks, Jasmine, for the introduction. And I would like to take a few minutes to tell you about the company MakerBot and about the technology in general. And then I will hand over to Dr. Thieringer. Okay, so the company started in 2009, so a relatively young company, you would say. And MakerBot started selling do-it-yourself 3D printer kits like the one you can see on the very left here from 2009. And then we subsequently released more advanced versions of this machine. The third generation was already available either as a do-it-yourself kit or as a fully assembled 3D printer. And then came the fourth generation, the very widespread and well-received Replicator 2. And at that time, since 2013, MakerBot is a subsidiary of Stratasys Limited, which means that now we're all employed by Stratasys and we can work together with them and profit from the decades of experience that they have. Then we released in 2014 the fifth generation of MakerBot Replicator 3D printers. And these are still the machines that we offer today. We have over 100,000 3D printers worldwide installed, so we have currently the largest installed base of 3D printers in the world. And we also run the largest online community, which is called Thingiverse. You can see a couple of images here. There are over 1 million designs uploaded on Thingiverse and available for everybody to download, and people are using this. There are over 1 million downloads per week as well. Okay, I would like to take a few minutes to tell those of you who don't know yet some details about the technology. The technology that all MakerBot 3D printers are using is called Fused Deposition Modeling, or FDM for short. I'm probably going to refer to FDM quite a bit in the next few slides. It is the most widely used 3D printing technology. Currently, it was invented and patented by Stratasys in the 1980s, and works like you can see here on the left. So the replicator works with some thermoplastic filament, which is moved through a device called an extruder. I'm going to explain this on the next slide. And the objects that you want to 3D print are principally built layer by layer by adding one layer onto the next and thus subsequently building up a three-dimensional object. The most common materials that are used in FDM technology are PLA, which is a polylactic acid, and ABS, acrylonitrile butadiene styrene, but there are also many other thermoplastics that can be used, and that are, some of them are offered by Stratasys, for example. Okay, I'm explaining the extrusion process in a little more detail. Usually the thermoplastic comes in a wire of a diameter of 1.75 millimeter, which is called a filament. I might refer to this as a filament sometime later on. And this material is then pulled through a device called the extruder, which pulls the solid filament and then melts it, pushes it to a hot through a hot nozzle at the end, and thus extrudes molten thermoplastic. The size of the nozzle is typically 0.4 millimeter, so a little bit less than a half a millimeter, and that determines the dimension of the smallest feature that you can print. So the smallest feature of material which is there is 0.4 millimeters. You could in principle make gaps which are smaller than that, but the biggest positive feature is 0.4 millimeter. And the nozzle size also determines the kind of layer heights that you can make. So the resolution in the direction of building up layers is determined by the width of the material that you're extruding, and that is typically 0.1 to 0.3 millimeters. And the fifth generation of MakerBot Replicator 3D printers have the Smart Extruder Plus, which and a technology that we developed that allows you to quickly exchange the extruder, which is the part of the 3D printer that typically has the most wear and the most it's the most easiest part to fail in the long term. So if you want to run your 3D printer for many thousand hours, then this would typically be the part that at some point would fail you. But since we have the Smart Extruder Plus, it is very easy to exchange it quickly and minimize the downtime of your 3D printer. Okay, I'm going to take a few minutes to talk about the general workflow. You're always starting with some kind of three-dimensional geometry that you have to define in some way. Most typical ways to generate this are a 3D CAD program. There are many, many different computer-aided design programs that you can use, which would then be used to define a three-dimensional geometry. Other ways to get to a three-dimensional geometry include surface 3D scan. Like, for example, with the MakerBot Digitizer, you can make a three-dimensional scan of a physical object, or as Dr. Thieringer is going to show you, that you can derive this from three-dimensional tomography data, like a CT scan or an MRI scan. This data now needs to be converted into a format that the 3D printer can understand. And that is, in our case, the quasi-standard is the STL format. The STL format is a very, very simple data format, but it is used for compatibility reasons still. And I show you here on the left in a schematic, whereas most CAD programs can, for example, have a perfect cylinder, a perfect sphere. The STL format is always an approximation with triangles. So a sum of triangles in space that are connected to each other define your geometry. So an STL file will always be a discretization of the object. This STL file is then loaded into the 3D printing control software, which is in our case the MakerBot desktop software, where you can plan your 3D printing process. So you can scale the object, you can change the orientation into an orientation that is suited best for 3D printing. You can change the printing diameters, like, for example, the layer thickness that I've been referring to. And then the computer will create commands for the 3D printer. So the 3D printer itself just accepts very simple commands like go in that direction, extrude, stop extruding, now go into a different direction, now move to the next layer. And the computer has to generate these commands, and this is done by taking the geometry and cutting it into slices and then generating the machine code for each slice. This is why this part of the process is often related to as slicing, as you can see here schematically. The object is cut by a plane, and then for each plane the machine path is generated. We have many different applications for FDM 3D printing, as with the MakerBot Replicator 3D printer. For example, there are a lot of applications in prototyping, where people are most often benefiting from the fact that with a MakerBot Replicator 3D printer you can print quickly and cheaply, and so you can have a lot of design cycle iterations for each product, which gives you a better feedback and still a shorter time for going to market. We had a webinar about this last time, which you can find probably somewhere on our website. Applications in the prototyping include functional parts like adapters, holders, casings. For example, this is a picture from a story that we have with the company Bosch from Germany, where they use this for electronic casings. Or, like I said, design iterations and evaluations, or models for presentation and demonstration for like a customer meeting or something like that. We also have a lot of applications in the education range, for example, schools, universities, but also very recently we see a lot of applications in the industrial education in Europe at least. The applications in the classroom include individual learning aids, like for example a learning aid for the blind, where kids can feel and so haptically, tactically understand shapes that they otherwise could not grasp, could not see, and other examples that I'm not going to refer to. MakerBot has created a teaching handbook called MakerBot in the Classroom that has been translated to 7 languages now, for example also German and some other European languages, and we're also working, like I said, in the industrial education area with companies like Hoffmann and Merck. But of course 3D printing in general is very well suited for anything where you have a low volume of production, so like a quantity of 1 or only a few pieces, which have to be very individualized. And of course this is the prime application in the medical case, where you always have individualized products for the patient. Like for example, you have anatomical models or orthodontic or orthodontic parts. But Dr. Thieringer is the expert in this, so I would like to hand over the presentation to him. Thank you.
Okay, Jochen, hi. Dear all, just a second, and you will see what I'm going to present. Welcome to this webinar presenting applications in medicine, because I think 3D printing in medicine is a very important part of the 3D printing in general view. My name is Florian Thieringer, and I have the honor to show you some applications. Today I would like to show you the basic principles of 3D printing in medicine. I would like to show you that you know more about the creation process from DICOM images to realistic 3D models. That means how do I get from a medical image a realistic 3D model? How is it done? Actually, you should know after this presentation how you can start from scratch with working with medical imaging data and design your first models. And at the end, I will show you some typical applications of 3D printing and craniomaxillofacial surgery. At the end of this presentation, we will have a question and answer section. If you have any questions, just put it in the chat box, and we will answer them later. We are located in Switzerland, in the mid of Europe. It's a quite small country, but highly innovative. Basel itself is beautiful, with the River Rhine and a very old university. But on the other hand, we have a really modern and innovative university hospital. that is one of the largest hospitals in the north of Switzerland. And there at the Department of Craniomaxillofacial Surgery is where I work as a consultant. And on the other hand, I'm the head of a research group for medical additive manufacturing at the Switzerland Innovation Park at our high-tech research center, which is a part of the Department of Biomedical Engineering at the University of Basel. One of the key points, which is quite extraordinary, is that we work in a very interdisciplinary or transdisciplinary research community at this center, together with different groups, for example, specialists for image-guided therapy, biomaterials, medical imaging, which is crucial for getting beautiful 3D models out of medical imaging data, and of course also technologies for tissue engineering and other groups that work together in this building. So if you're in Basel, feel free to get in contact with me. I will be happy to provide you a short insight to see what we're doing there. But on the other hand, you're not a medical specialist, but I saw there were some medical specialists that were applying for this presentation. So hi to all colleagues. But to the rest, I'm going to explain in short what oral and craniomaxillofacial surgery is. Mainly, we are the doctors who take care of everything that has to do with your face, with your teeth, with the bones in this area. Not with the brain itself, but the structures that are in direct neighborhood to the brain, they are also very relevant for our business. We take care of, for example, skull deformities in the craniofacial surgery. We operate if you have problems with your jaws, if you have sleeping disorders, snoring at night, or if you have a tumor in your face or in the oral cavity. And what is also very important, or quite a large part of our daily business, this is the traumatology of the facial region, where we take care of you if you have a severe accident or you break a bone of your face, then we take care of that. That may be one cause why we have been working with imaging technologies and 3D imaging technologies for a very long time, since the invention of the 3D reconstruction, or based on the computer tomography. We use this kind of technology to visualize injuries or diseases of the facial region, which is really complicated. You have a lot of nerves and very delicate structures of which you have to take care. And therefore you can imagine that for us it's very helpful to have the option to see the patient itself in a visual representation. On the left you see a very severely injured patient, maybe caused by an accident. The skull is fractured several times, and that can be caused, for example, by a high velocity trauma. For example, if you have a car accident, you don't wear your security belt, then this kind of fractures can be the result. And what we do is to fix this, these fractures, these broken bones, by titanium plates that we place in the correct position and stabilize the broken bones. And as you might know, the bone is covered by soft tissue. So we use approaches from the oral cavity, or very small approaches from different anatomical regions, that the scarring after such an operation will not be too big, and the patient will be hopefully completely reconstructed. When you compare the traditional conventional X-ray in 2 dimensions, like this X-ray where you can see the titanium plates, it's quite hard for us to see if the result of the surgery is okay, or if there are any changes that should be done. The CT scan, which you see here, it's a reconstruction, and you see from the front to, on the patient, will bring some more, will provide some more information about the reconstruction. But still, it's a 2-dimensional image that you can go through layer by layer. And the next step, the 3-dimensional image, which you can see here, which is a reconstruction of the layer, the layers of a CT, a computer tomography, a CT scan, that provides quite a lot of information for us, which is very helpful if you have patients that need to be reconstructed because of a severe accident or a tumor. This is a patient I operated recently. He had an accident several years ago, was operated, and the trauma and maybe also the operation itself, he had a facial asymmetry that was reconstructed by the use of a patient-specific implant, which was not 3D printed but milled. I hope in the future we will be able to print thermoplastics that can also be used in reconstruction or bone-like structures. And we use this model to plan the surgical procedure itself and to have a look at the patient-specific implant it will fit into the anatomical region. So for us it was really helpful to have a 3D image, a 3D model, not only a 3D image. The one you just can see is not comparable with a model that you can hold in your hands, which has the exact size and the exact anatomy of the patient you're going to operate without touching him before. So you can imagine the 2 dimensions, 3 dimensions, being able to provide, for example, a 3-dimensional model like that one, or here where you can see the skull of the patient, and you can plan your operation directly on the model, is very helpful for our discipline. Not only for our discipline, but also for other medical disciplines. And most of you maybe do not know that 3D printing is a quite old technology, invented more than 30 years ago. And in medicine, especially in craniomaxillofacial surgery, we have been using it nearly since the year of the invention. Some years later, we started to use that kind of technology for our purposes, to plan operations and for many other things. 3D printing itself is, if you have a look at this slide, is a very disruptive technology. For the year 2025, the impact, the global potential economic impact is estimated to be around 550 billion US dollars, which is really impressive if you compare it to the other technologies that are listed on this slide. So 3D printing is not only in industry a very important technology, but also in medicine. Before printing was getting bigger in medicine, 3D milling technologies have been used to produce patient-specific models. Here you can see a milled out of a foam block, a milled skull model. It's from 1987, so it's quite old. And that one, which was printed or designed and printed by my boss, Professor Hans-Florian Zeilhofer, is from the 1990s. It's a stereolithographic skull model, which was is still really expensive, but in these years it was really expensive to be produced. That is a model we use to plan a surgical operation to reconstruct the zygomatic bone, which you can see here in gray. That model was printed by a research colleague of mine, Ralf Schumacher. And if you compare the reconstruction of this defect area, this patient had to be operated because of a tumor in the area of the zygomatic bone, which was a quite good result, but still the patient had severe aesthetic and functional problems after the operation compared to the three-dimensional planned and 3D printed reconstruction method. You can see the differences. It's really a big benefit in medicine to be able to produce models to plan surgical procedures. And it's not only plastic or titanium, which we use in the medical field. We also use ceramics and other materials that can be printed. So how do we get those models? I already have shown some, and I'm going to present now the workflow. It all starts from the data acquisition, which means we need something that is showing us how the anatomy of the patient is actually at the moment of the examination. We will get images from CT scans or MRIs, mostly CT scans or digital volume tomography, which are also possible to be reconstructed three-dimensionally, but mainly we use CT scans to reconstruct virtual 3D images. And this step is called segmentation. Then from this step on, we are able to produce the 3D model. So first we have a virtual model, then we are going to design the realistic model, and at the end we have the model in our hands and we are able, for example, to simulate surgical procedures directly on the model before touching the patient. So step by step, the patient will be put into a CT scanner. We will get the DICOM images. It's a standard in medicine for digital images. It's imaging and communication in medicine image format, which can be transformed to a 3D model. This step is called segmentation. We have different software solutions that can be used. I will show you later on in a step-by-step video how this will be done. You have, of course, software, professional software, which is medical certified, and you have open source software that can be used. So to have your first models, you just need a CT scan, you need some open source model and open source software, and you need a 3D printer. And today you could print out your own skull model like this one. And what we do with the 3D images that we have designed or generated by the software is, for example, planning surgical procedures on the computer. But we can also put it in the slicing software, as Jochen already showed. And the next step will be the 3D printing process. For example, the FDM printing with thermoplastic filaments. What is very important in medical printing, 3D printing, is that you try to get the best imaging, radiological imaging data as possible. The data shouldn't be too old. That means, for example, if you want to print out a tumor, after some weeks it can grow. So depending on what you're going to print out, it's really crucial to have fresh CT scans, and or if you want to print out, for example, a skull model of a child, then it's also important to use the most recent CT scans, because after half a year the skull may be quite bigger than before. And which is also very important, that you reduce the influence of artifacts in the segmentation process by a standardization of the positioning of the patient. That means you have scanning protocols. I shouldn't go into detail, but to know that the quality of the imaging data should be very good, should be important. Here, for example, you can see the model of a fractured mandible model that will be put on the build platform, the virtual build platform of the slicing software. The software will prepare a file that will be transferred to the printer, and the printer is able to print out the model itself. That will take from model to model, from volume to volume, depending on how big the skull, for example, is going to be, will take several hours and will take quite an amount of material. This mandible model, which is in quite high detail, takes around 5 hours to be printed out and uses about 50 grams of material. So you have different printers that can be used for this approach to produce models. For example, the single extruder printers that use support structures that can be easily removed. As you can see here, for example, that are available and are used by us. We also have printers that use a second extruder if you want to print out, for example, 2 colors, or if you want to print out, of course, dissolvable support structure, which can also be a benefit and advantage if you don't want to remove all that support structure that is needed to print out that kind of structures. So here is a short video where I'm going to show you and comment how you will get actually out of those CT scans a 3D model. First, you start with the DICOM image folder, which you which you get usually from the Department of Radiology with the images. Depending on the anatomy of the resolution of the slides, the size is between, let's say, 100 MB to several hundred megabytes. You will import this software in a segmentation or DICOM viewer software. In this case, I used on my Mac open source free available software which is called HOROS, where you can visualize the CT scans. This is a cranial CT scan. You can go through the CT scan and see here, for example, the brain, the eyes, and different other structures. You can change the view. Now we have a look from the front on the patient. You can see the bone, which is white in this area, and you see the soft tissue, which have tissues which have different gray shades on this image. And those different gray shades of a CT scan we use to isolate the region of interest or the structures of interest we would like to print out. Here you can see, for example, the vessels, and you see a part of the gantry. It's the part where the patient is lying on, and that is what we would like to remove from this data set. So we have a scissor tool. First of all, I'm going to isolate the bony structures from the soft tissue. It's really easily be possible to remove the soft tissues, and then you have a scissor where you can remove the structures that you don't need. You can isolate the region of interest. Here, for example, the skull. And in the next step, we're going to produce the virtual image of a skull. Then, the next step is surface rendering. In the different software solutions that we use, we have professional software suites which are needed for if you, for example, produce patient-specific implants, but just for printing out skull models, it's not needed necessarily. For example, 3D Slicer or Visalius, which is a software solution from Brazil. You are able to isolate the bony structures from the rest of the skull. And here you see you define an area of density or of grayscales or whatever the CT scan is showing you. And with that, you're able to isolate and to generate a 3D model. The soft tissues are thrown away. The air or the structures that are not interesting can be separated from the bony structures. So here you already see a model that can be exported as a STL file. And that is what I use. Here you see the size, it's around 70 megabytes that I use to go further to prepare the skull for 3D printing. Here, for example, which is also open source software, is Mesh Mixer, which can be used to isolate, for example, the skull from the isolated particles that are sometimes in your data set that shouldn't be printed with that skull model. So you can select the bone of the skull itself, and then you remove by the inversion of the selection the flying particles. So you can use this kind of software to clean the model. You can smooth it. You can reduce the size, and after that steps, you're going to export it. Here I'm going to remove it, and in another step, you're able to export this skull as an STL file and import it in your printer software. I will skip the next slide. Sometimes I use NetFab. It's also in this basic version, which is a little bit limited in the functions, it's available for free, and there you can clean up the data and can cut out parts that are not used. They will close the surfaces, and that model itself will be imported in the MakerBot printing software or in any other printer or slicing software. And you see the skull itself is positioned, it will fit on the build platform, and now you just have to start the slicing process itself. Usually you have really good results with the standard layer resolution of 0.2 millimeters and the infill of 20%, and after that you have the final skull that can be printed out. So it's really easy to get your own skull in some hours. Okay, so just a short insight how to produce your own models. It's a little bit fast step, but you will find in the internet a lot of instructions how to continue step by step to print out anatomical models. Here you see, for example, the printing process. It's faster than usual, where we print out mandible models, so for reconstruction after tumor surgery, and for that standard printers are used. We usually print 90% of our models with consumer printers. Before we started using consumer printers, we wanted to evaluate if those printers are suitable for the use in the clinic. So we compared by surface scanning if the resolution is good enough and if there is no warping or other effects that will cause inaccuracy. So those studies have shown that the resolution is really excellent, and the models can indeed be used for example, planning operations, surgical procedures, for pre-bending, scan titanium plates, or a lot of other applications in medicine. So we use mainly those 3D printed models for education. It's very important for training our residents and our students. We use those models to explain the patients what we're going to do, especially in complex surgical procedures. We have those models and can explain the patient on his model, his realistic model, what we're going to do. This is not a maxillofacial model, but here, for example, you can see it's a skull model with an impression of the frontal bone. And that kind of models we can use for planning operations and also for explaining to the patient what we're going to do. But what is also very important is to produce drill or cutting guides that will show us where we have to put our screws, or we have to cut the bone. And what is also very, how can I say, futuristic and useful is to print the guides or the plates, the titanium plates or the reconstruction models by the printer itself in titanium, for example, or in different other biocompatible materials. So I think the part of the bioprinting or hard or soft tissue replacement will be something that will be a part of the modern medicine in only a few years. And the parts of, or the different parts of the maxillofacial surgery where we use that kind of models is, of course, dental implantology, where you can plan how to put the implants and where to put the implants, and use, for example, printed guides that will show you where you have to put it regarding the anatomical structures, or in traumatology, as I already mentioned, in surgical procedures where you have to cut the bone and put it in a new position, like in the orthodontic surgery, or in different other parts of the surgery. Here you can see a patient where a part of the skull is missing. It's a planning model for reconstruction of a patient with a huge tumor in this area, where we did the resection, and now we're planning how to replace this missing part. Or here, for example, a patient where we used this 3D printed model to pre-bend a titanium plate that will replace the floor of the orbit. And here you can see the model of a patient-specific implant that we used for replace a part of a tumorous bone of the midface. Another patient, fractured mandible, usually should like more or less like here, but before surgery the patient got a CT scan, and we reconstructed the CT scan and used this model to explain the patient and the residents what we're going to do. We were able to pre-select the best fitting titanium implants that we wanted to use for reconstruct the mandible, and therefore we were able to successfully perform the operation itself. In a collaboration with a university clinic in Germany, in Frankfurt, we produced three-dimensional models for the training of residents. They can use those models to learn the different pathologies of the skull, and of course they can also use those skull models to plan and to prevent titanium plates, which is used, for example, if you have a fractured bone in the facial area, as I already mentioned, to fix the bone in the right position. Here, for example, a patient with a fracture of the zygomatic bone, you can maybe see here the line of the fracture, which is going through the orbit and through the zygomatic bone itself. And quite easy step is just to mirror this 3D model. You see now the fracture on the other side, and we can use the healthy side as a template to prevent those titanium plates, which is not very complicated, but on the other hand, for residents, it's a good way to train without the stress in the OR, to train the pre-branding procedure itself. In Switzerland or at the university hospital, the minute of operation time in the theater will cost around, let's say, 50 francs, which is around $50. And you can maybe imagine that just half an hour less of operation time is quite a huge amount that you can save if you prevent, for example, titanium plates, especially in reconstruction of the mandible. This is crucial because the bending itself takes quite a lot of time. So you can see a resident who is bending in a very relaxed atmosphere the titanium plates. In the OR, it's always a little bit difficult to excuse me. It's always a little bit difficult to bend those plates without the stress, and here you have enough time and can relax. So on the next slide, you will see a template that can be used, for example, for reconstruction of titanium plates for the orbital floor. And here we just print out a small part because it will just take about 1 or 2 hours to produce this titanium, this plastic model to prevent the titanium mesh for reconstruction. Maybe you can see it. This is a template we can use to prevent titanium plates. On the right side, you see this titanium mesh, and on the left side, the template. And here you see the 3D imaging after the operation. The mesh is fitting perfectly in the position that was planned to be replaced. Another case, for example, for reconstructive surgery, where we use patient-specific implants, 3D navigation for removing tumors. Here you can see a tumor which is marked on a 3D navigation system, and we can use titanium plates and also 3D models for the reconstruction of those tumor patients. As you can see here, for example, this plastic model is very useful to plan that very complex kind of surgery. Here you can see the patient-specific implant, which is a which is a PEEK implant milled out of a PEEK block. And here the next patient is a patient that operated recently. You maybe remember him from the beginning of this presentation, who has quite large asymmetry or defect in this area that was replaced by a patient-specific implant. Here, a 3D printed model, which you can see here. And here you can see the patient-specific implant, which was milled out of a PEEK block. And the surgical procedure itself was quite quick, and there were no surprises because we have the model, we have the patient-specific implant. We were able to plan the surgical procedure itself. So it's a really a benefit for the surgical procedures. Here, a low-budget approach for a skull reconstruction. This operation I performed in Nicaragua. You see the defect of the skull of this patient here, maybe. There was not an accident, but the patient was hit down and severely injured, and the result was asymmetry and a quite big skull defect, which you can see here after we got the 3D scan, the CT scan. We did a reconstruction of the defect. We separated the region of interest. You see here the 3D modeling program, and we printed out the part of the skull with a defect. And this is the part, the resulting part that we printed out. And we used it as a guide to preform a titanium mesh that was used to reconstruct the skull, which is done by a coronary incision. Here you see the defect. I discolored it. And here the titanium mesh was like fitting perfectly because I was able to pre-bend it on the model, and then just had to put it in the position to reconstruct the skull. And then we were able to put in like a surgical cement. And after that, the patient was completely rehabilitated. The defect zone was covered, and the procedure was successful. Here another example. A tumor in the mandible, which is going to be resected. We have to pre-bend this titanium plate, which takes usually quite a lot of time. With that model, it's a really easy step, and you can use this. You put this in the sterilization, and then you can use it in the operation room, and it's already pre-formed and perfectly fitting to the patient anatomy. Here, a patient with a fracture of a highly atrophic mandible. Most of the teeth are missing, and the mandible is very, very weak. And you see maybe you can see the fracture in this area. We used 3D reconstruction and printing to put back the parts of the bone in the right position. The blue material is used to fix those parts in the right position, and that mandible was being used. This mandible was used to preform a titanium plate, like I've shown you before. You can of course also use 3D software to put to reduce the fracture. But this way of pre-bending plates is also very useful for surgical procedures. You will save a lot of time with that kind of preformed plates, and you can use smaller surgical approaches. Like here, you see the patient that was operated. It's an approach from this side. And we showed the fracture itself, fix it with a wire in the right position, put in the titanium plate that we pre-bent on the plastic model, and we just had to put in the screws, and that's it. Here you can see the post-operative cone beam CT, which shows you a perfectly fitting plate and a perfectly reconstructed mandible. Next step, of course, or what we also do, is in cooperation, or mainly the University of Applied Sciences produces titanium implants printed out of a titanium powder, and that kind of implants can also be used, of course, to fix bone fractures or to reconstruct missing parts of the skull or other regions. They're all perfectly fitting because we use the patient's anatomy. It's very realistic and accurate, and those implants are the best way to reconstruct defects. So here, for example, you can see that kind of printed plates. You just put it on the defect zone and you're able to put in the screws, and then you have the fracture fixed. You can print out any way of design that you like. For example, here the mandible reconstruction plates, as I already mentioned, to fill out those gaps and to stabilize the mandible after tumor surgery. And what is also something we are quite intensively doing research in is the 3D printing of a thermoplastic material that can be implanted into the body, which is at the moment PEEK. So it's quite a big task to get this PEEK parts in a quality that can be implanted. We're working very tightly together with a company in Germany, Indmatec, to produce those to guarantee a quality standard that those implants can be officially certified for implantation, and working very hard on this topic. Here, for example, you see a skull replacement plate made out of PEEK, this medical grade thermoplastic. Or here you can see a part of the zygomatic bone, as you can see here, also printed in PEEK. The next steps will be, which is also a part of our research, the intraoperative 3D scanning of defect zones, and this is something which is already the present, but also will be the future, because there are also a lot of challenges that are facing us. That is the printing of 3D patient-specific implants that are going to be a realistic replacement for missing parts like bones or organs, or combined tissues like bony structures that are stable enough to replace parts of the extremities, for example, or the mandible, but also will be completely integrated in the bone that is around of this implant. So at the end, the limitations and need for further research, as I already mentioned. Crucial is the data acquisition. We need protocols that have a low dose of X-rays. The software needs to be easily to use. It should be designed for surgeons, not for engineers, as well as the hardware. The materials are crucial. That means we need biocompatible, certified, or in the States, FDA certified materials. And what is also something that should be optimized is the processing and the production time I think in future we're able to produce patient-specific implants or models in a really fast time. And that's what we are facing. Of course, the production costs will be or should be optimized. I think with the consumer printing, we have already an approach to produce very cheap, cost-effective models compared to professional production machines that cost thousands of dollars. We are able to produce for just a few dollars very realistic models, and this is also something that is a great advantage and benefit of the 3D printing of that kind of models. Another part or another topic of research are the bioimplants, bioprinting, and 3D tissue engineering. I think the future will show what is the potential of this kind of manufacturing method, and what is also necessary that we work transdisciplinary, cooperate, and develop together with different specialists like material scientists, medical professionals, regulatory professionals, engineers, whatever, to get the best out of this field of research. So at the end, medical rapid prototyping is a perfect match for the virtual planning. Not only the visualization is important, but it's also important to be able to hold a model in your hands. It's suitable for all medical disciplines, so not only for surgery, but also for different other disciplines. It is a huge advantage and benefit for the patient-specific medical care. And we don't need very expensive printers for the production of basic models for education or for producing demonstration objects. We will improve with 3D printing in medicine the patient safety and the quality of care itself. That means, for example, the patients don't have to stay that long at the hospital because the reconstruction is much better than it was used to be with the conventional methods of surgical procedures. We have less treatment costs. This is one result of the reduced length of stay. And my vision will be, what my vision is, will be the integration of medical printing labs in the hospitals. So here, for example, at the University Hospital in Basel, we have a joint project together with the Department of Radiology, where we have several printers in our 3D printing lab in-house to be able to print on-spot patient-specific models for the different disciplines. That's crucial because you need a very short time to produce that kind of models. You cannot wait for weeks for external companies to deliver the patient-specific models. Mostly, for example, in trauma patients, it's important to get this in a short time frame. And at the end, of course, of this presentation, I would like to offer you cooperations and platform to exchange the knowledge. And of course, I am really interested in your questions. And I think we are a little bit over the time, but I'm really keen on knowing what your questions are. So thanks a lot. And I will get back to Yasmin and Jochen for the question part. Hello?
Yes. Thank you very much, Florian. It was a really, really interesting presentation from your side. And of course, we have some questions for you. One question I picked is from Belarus. His name is Alexander Savitsky. And he wants to know, or he stated that their medical university is interested in 3D printing of skulls and bones, but they say the quality of MRI files is not precise as they need to be. How can we deal with this issue?
Well, actually, MRIs are mostly a very good way to represent soft tissues. So if you want to use that kind of imaging data for printing out soft tissue structures, MRIs can be used. But usually we use CT scans, for example, to produce that kind of patient models. So it's I think crucial to know what the indication will be. If you want to represent, if you want to, for example, print out bones, an MRI scan will not be the right solution. So I think the first way should be to talk to a radiologist, how to get the best imaging data, and that can be used to produce 3D files, depending on the indication.
Okay, thank you very much. I hope, Alexander, that this question is now answered accordingly for you. If not, please let me know. I have another question from René Louis Gutierrez. He wants to know.
I know him, yes, he was.
Okay. Okay, regards to Professor Zeilhofer, and also his question is, how long does it usually take to print a skull model?
It takes around, depending on the volume, of course. For example, where's my model? I've lost it. Here it is. It's a children's skull that may take about maybe 12 hours. Yeah, I think about around 12 hours. That's why I, for example, cut the skull in a way that the region of interest is being shown, but on the other hand, the volume is not too big. So if you want to speed up the printing process itself, it's necessary to smooth the object itself and to reduce the complexity of a model, and, for example, to decrease the size of the model. That will speed up the printing time enormously. For example, that one here is being printed in, let's say, 2.5 hours maybe, for a reconstruction of the orbital floor. And this is a time frame which is in-house acceptable, because when we have a patient and the patient needs to be operated, we have normally enough time to produce that kind of model.
Perfect. So, are there any more questions from our audience? Yes. I have a question from Martin Hurni. His question is why to choose the FDM technology, and why is this the best option? Because of the cost? Is it cost effective, or why do you choose FDM?
FDM is a very cost-effective 3D printing method. The material itself is quite cheap, so I think there's no printing method, Jochen may correct me, but there's no printing method that is cheaper in materials than FDM or FFF printing. And the printer itself, or the printers itself, are quite, how can I say, reliable. The other technologies that are comparable to the FDM printers we use, they have several disadvantages. For example, the build platforms are smaller, the material is really expensive, or for example, the production of the models, which is also crucial because it needs to be very reliable. When I start a printing job, for me it's necessary that I can pick up the model after several hours, and it's like I imagine it to be. It shouldn't be like completely wrecked or whatever. And I think the FDM process is in that case superior to other printing methods. And the price of the printers itself are also, I think, very relevant in this for this question. So for us, it's I think the best way of producing patient models.
Perfect. Thank you very much. So, is there still a question from your side, from the audience? I don't see any more questions.
Excuse me, I did see one. Do you use plastic 3D models as temporary implants, or is it not possible? This was
no. The problem in that case is that the materials we use here, for example, for printing out that kind of patient models, they're not certified for this purpose. So you need certification, and it needs to be biocompatible to be used as a spacer or a temporary implant. I think the future will bring solutions for this kind of problems, and there are already some materials, not in the FDM sector, but in other printing technologies that can be used for producing that kind of spaces. But compared to the FDM process, it's the materials and the printers are much more expensive, of course. This is the professional area of printers. Yeah.
Okay, thank you. So as far as I can see here, what program you recommend for converting DICOM files for STL? Asks Pavel Kaida.
So if you just would like to start from scratch and you just want to produce a model and you want to learn the process itself, then there are several open source software solutions that can be used. As I've shown, Horos, for example, which is comparable to Osirix on the Macintosh platform, can be used. Or, as I mentioned before, the Slicer, it's called Slicer software, can be used. Or, for example, there's a Brazilian group that developed open source software which is called Invisalius, that can also be used for segmentation. And if you would like to get into the business, 3D printing and professional use of that kind of models, you have a lot of high turnaround of models, then there are several commercially available software solutions like the Materials software suite or other software solutions that can be used to print out models or to segmentate and print out models. Okay. And maybe to mention, if there are specific questions, you feel free to send me an email, and I will try to answer this question for you.
Perfect. Jochen, do you see another question?
Yes, there have been two questions coming in from Neha Sharma and Will Glass that are both regarding the accuracy. So if you print with FDM, I think, Florian, you already answered this partially, but could you comment once more on the accuracy of the print from an FDM printer, such as the MakerBot Replicator, if you compare it to the original CT data?
Yeah, what we use usually for CT scan, a slice thickness of 1 millimeter or 0.75 millimeters, and the 3D printer or for example the MakerBot 5th generation printer prints up to 0.1 millimeter slice thickness. That means the resolution of the printer itself is higher than the resolution of the CT scan. That means you will have enough accuracy to print realistic models without quality drawback. And what can also be crucial is to for example, I never use the high resolution to print out those models because you can imagine high resolution is also increasing the time, the production time. So I use usually the 0.2 millimeter resolution to produce models. We, as I've shown on my slides, maybe it was a little bit too fast, but you saw that we scanned the objects by surface scanner and compared it to the original file, and the accuracy was astonishing high. It was below 0.2 in most of the parts or the points we were measuring. So the FDM method is regarding the accuracy enough. If you want to use it for example, dental applications, it may be not enough, but usually for printing out anatomical structures like bones or for example, hard models or whatever, the accuracy is enough.
Okay. So,
Jasmin, do you want to? Please.
Again, what?
So we have a couple more questions coming in. I think we have to limit it at some point. One question from Alexander Savitsky. What type of technology materials are certified for using as implants?
What materials or which?
What technology? So probably what 3D printing technology, and what materials are already certified for implanting?
The implants, the titanium implants that are being produced as implants, patient-specific implants, that are produced by the selective laser melting technology. That are machines that are really expensive, and they need to be certified for this topic. So, as far as I know, there is at the moment no alternative to print out implants, for metal implants, for example, to be implanted in the patient. There are some ceramics that may be used, and there may be possible to be a replacement part for patients, but plastics that are being printed are, as far as I know at the moment, not certified to be implanted forever. As a temporary solution, there are some materials, but not for a solution that will last forever.
Okay, so we have one more last question before we have to finish our webinar. It's again from René Louis Gutierrez, and he's asking if the MakerBot 5th generation printer is comparable to a medical grade 3D printer.
Yeah, well, actually, it's a little bit difficult because what is meant by medical grade? Yes, it's like yes and no, because at the moment, of course, you cannot use the MakerBot printer, for example, to produce a patient-specific implant that is being put in the patient. And this is very experimental and not officially certified. But if you compare it by resolution, then it's of course comparable to professional machines, or to machines at a higher range of costs, of course. That's why we use, for example, this kind of production machines for producing patients models.
Okay, so we have more questions coming in, but I think we just have to stop here. It was very, very interesting. Thank you very much, Florian and Jochen as well.
You're welcome. Thank you.
And yeah, we will send you a recording after this webinar automatically. And if you have any more questions, please send them over to me or to Florian as well. I think your contact details can be found on your website, right? On the website.
Yes, on the website, and I'm not sure if on your page is also my contact details, or just put it in Google, or it's Swiss minus mam.ch, swissmam.ch is our website of the research group. If you just Google me, then you will find the contact details.
Okay, perfect. So thank you all very much. I'm happy that it was that interesting, and see you again soon. Thank you.
Thank you. Bye bye. Have a good day.
Bye. Bye.